All right, team, welcome back. This is kind of an exciting day for me because this is actually the last video um, I'll be making, or the last set of videos I'll be making, because all the stuff from chapter 12, I still have that from last spring. Okay, so let's start. We're going to talk about optimization. So it's chapters or sections 11.7 and 11.8, but we sort of put them together. Okay, or I do, and I add a little flavor of my own to it. So do be sure to watch these videos. I think there's a little extra in how we're going to solve the problems. It'll make it a lot easier if you follow along the whole thing, okay? So let's start with just a refresher of one-dimensional optimization. Okay, so a typical or a canonical problem of one-dimensional optimization is max optimize f of x equals x squared on the interval, let's say -2, 3. Okay, so there were sort of things we had to do. Find critical points first. So that is f prime of x equals 0, or f prime of x doesn't exist. Okay, so in this case, we're going to take f prime of x equals 2x. So that means x equals 0. And then we're going to take and we're going to find f of 0 and f of the endpoints. So we take it at the critical points and endpoints. Okay, and then we just compare. So that f of 0 is 0, f of -2 is 4, f of 3 is 9. So we have a local and absolute min here. Okay, and then we have an absolute max here. Okay, and then this one, you could say that's a local max. Let's not get there though. But one of the other things is that we also have, we actually don't need it here, but we can also have f double prime of x, if f double prime of x is bigger than 0, we have a local min. F double prime of x less than 0, we have a local max. F double prime of x equals 0, the second derivative test fails. Okay, so here, f double prime of x equals 2 is greater than 0, we have a local min. Okay, we already knew that from this information, but it's just another way to get that information. Let's just real quick graph this thing. Try that again. Okay, and so there you see what's going on. You have this local min here, an absolute max here, and technically we could say that's an absolute or a local max, but we'll worry about that later. Okay? All right. So let's look at sort of let's look at just this example in 3D. What does that mean? Okay, well, let's take a look at f of x equals x squared plus y squared. I'm sorry, f of xy equals x squared plus y squared. And we're also going to have to give it some sort of domain or range, or domain. Okay, so let's give it a domain of x squared over 4 plus y squared over 9 less than or equal to 1. Okay, so what's going on here? We have some ellipse. Okay, sort of go through in 3D. Terrible at drawing it, but something like that. That's our domain. And then we have the paraboloid. Okay, but it sort of conks out at the top here, right? Okay. Okay, now we're gonna do the same sort of thing. We're gonna find critical points. Critical points. Now, just like in the one-dimensional case, in the Calc 1 case, it's very similar. We're gonna find places where the derivative either equals 0 or does not exist. But now, instead of derivative, we're gonna use the gradient. The gradient of f, let's do that with a different font. The gradient of f is, of course, the partial with respect to x of f, partial with respect to y of f. Either it equals 0 or does not exist. Okay, so for this case, gradient of f equals derivative of this with respect to x is 2x. Derivative with respect to y is 2y. So our critical point is at 0, 0. Okay, so far so good. Let me move this to the next page. Okay. Now let's not talk about the second derivative just yet. We'll get there. But let's talk about the boundary. So the boundary is given by this ellipse. Okay? So what we're going to do, we're going to have to look at what happens on the boundary. Well, we're going to have to parameterize that boundary. Okay? I don't need to worry about where it starts or whatever. It's just whatever I want. I'm going to use the simple cosine and sine. So I'm going to say, let's parameterize the boundary. So we're going to use x, let's call it theta, equals 2 cosine theta. Y of theta equals 3 sine of theta. So now we're going to plug this into my z function. Okay? That's x squared over 9. Sorry. X squared plus y squared. So I'm going to plug that in. So I'm going to get 4 cosine squared of theta plus 9 sine squared of theta. Okay, Now, I want to maximize on the boundary. I want to find the optimal solutions on the boundary. Okay, so we're going to take the derivative. This is now a, let's call it f tilde. Let's call it, like I said, f tilde of theta, okay, because we're writing x and y in terms of theta, okay, so we're going to say this, and this has a derivative in theta. Write that a little better, of 8 cosine theta sine theta, that gets a negative, plus 18 sine theta cosine theta equals 10 sine theta cosine theta, which, remember, sine theta cosine theta is 1/2 sine 2 theta. Okay, so when does f prime equal 0? So that's at 2 theta equals 0, 2 theta equals pi, 2 theta equals 2 pi, and 2 theta equals 3 pi. Because remember, we're looking, and 2 theta equals 4 pi. Because remember, theta here, I didn't write it, but I should have. Theta goes from 0 to 2 pi. Okay, let me move that in there. Okay. So this is theta equals 0, theta equals pi over 2, theta equals pi, theta equals 3 pi over 2, theta equals 2 pi. Okay? Now, we can take the second derivative to find what's going on, but we really don't need to so much. Okay, let's watch what happens. So what I'm going to do is instead, I'm just going to plug I'm going to plug these values in for x and y, okay, or to give me the points, okay? So theta equals 0. What point is that? Well, cosine of 0 is 1, sine of 0 is 0. So we're going to get 2 comma 0. Theta equals pi over 2. Cosine of pi over 2 is 0. Sine of pi over 2 is 1. So we're going to get 0 comma 3. Theta equals pi. That's going to be negative 2, 0. Move that right over here because it sort of goes with it. Theta equals 3 pi over 2. You can kind of guess where this is going. That's going to be 0, negative 3. So now I can plug those numbers in to my original z to find where I have maxes and mins. Okay, now, what's going on? We also have to compare it with the 0. So here we have a local local min. Here we have an absolute max. And all this is this is a minimum on the boundary. Okay, so let me go ahead just real quick, and I'm gonna summarize sort of what we've just done for in general. Okay, so same ideas in one-dimensional calculus. Given z equals f of xy, it should be continuous on a what's called a connected closed domain D. Okay, so connected means that it's like not in one, not it's only in one piece. And closed is sort of the same thing here where we have to include the boundary. Okay? Okay. Then all absolutes, maxes, and mins occur either just like in one dimension at a critical point or on the boundary. Okay, just real quick, what we did on the boundary is on the boundary is a one-dimensional, I should say on the boundary of D. Okay, and the boundary is a one-dimensional sort of object. So then that becomes a one-dimensional calculus problem. And you can do this in more than 2 dimensions. You can do it in, n dimensions and 10 dimensions if you want. And then the boundary becomes a 9-dimensional figure in that sense, in which case you do the exact same thing until you get down to the bottom. Okay? All right, I'll see you all in the next video.